So in this video, I want to talk about trying to achieve accuracy parity in this kind of scenario. Now, I should say you probably will not actually want to do it in practice. So accuracy parity is kind of like a dubious goal, probably. Possibly the predictive positive value parity is more important anyway, but let's say that that's what you want to do. So we're going to try to do that, and we're going to see what the consequences are going to be. Now, the problem is you're classifying members of group A with 84% accuracy and members of group B with 85% accuracy. Now, there is no way in this framework, at least, of increasing the accuracy parity. Now, you might imagine, collect more data, get something, but there's no easy way to increase this 84. So that kind of leaves us with saying, well, we want to make this 85 into an 84. Now, how might we do it if our classifier right now it can just say this person is going to be low risk or this person is going to be high risk? Well, we're going to have to say, well, with some probability, kind of swap the person out of the high risk into the low risk pool or vice versa in order to get this classification rate down to 84. Again, this kind of feels like you shouldn't be doing that, and that probably is the correct feeling. So this is just kind of like a mathematical exercise. So how would we do it, and how would we get the correct classification rate for B to be 85? Well, in order to do that, we'll just go back here and rewrite the numbers. So we're going to say, okay, so there's still going to be 100 people here in the pool in total. So what we want to do is we want to say, okay, so let's leave the 40 alone. So the 40 are the people who we said are low risk, and we were right. The 45 rather. We'll leave that alone. So we said 50 are low risk, and we'll still say not going to be arrested for all the low risk people. So we're going to be correct about 45 of them, and we're going to be incorrect about 5 of them. Okay, now let's look at the high risk pool. So for the high risk pool, we said about 50 will be arrested, and we were correct about 40 of them. So let's try and say, okay, so out of those 50, I want to say for some of them that they will not be arrested. Okay, so what they'll do is they'll say that for alpha times 50, say that they will not be arrested out of the 50. So for example, if I want to say that one person out of the 50, even though they're high risk, they will not be arrested, then alpha is going to be 0.02. So I'm going to say, okay, so about 1 minus alpha times 50, I'm still going to say that they are going to be arrested. So this is how much I say they're going to be arrested, and I'm going to be correct about 0.8 of them. Now, for alpha times 50, they are high risk. They have an 80% chance of rearrest, but I'm going to say that they're not going to be arrested. So I have just a 10%, so I'm going to say not going to be arrested. So actually, they have an 80% chance of being rearrested. So I just have a 20% chance of being right. So that's going to be 0.2. Okay, so I'm just counting all the people about whom I'm right. So this is the low risk people, and out of them, I'm right about 45 of them, nothing changed. Here, I'm saying I'm going to say that they will be arrested for 1 minus alpha times 50. If alpha is 0, I'm just going to say that yes to 50 people, and out of them, 80%, in 80% of the cases, I'm going to be right. So that's how many I'm going to be right about when I say yes to. I'm going to be right here. And then out of the pool of 50 high-risk people, I'm going to say no to alpha times 50, and I'm going to be correct 20% of the time. And my goal here is that this entire thing should be equal to 0.84. Okay? So now all that I need to do is I need to just solve this equation, right? So that's going to be 45 plus 1 minus alpha times 50 times 0.8 plus alpha times, so 50 times 0.2 would be 10, is equal to 84. So 50 times 0.8, that's 40. So that means, so I'm going to rearrange terms here, and I hope I'm not going to get anything wrong here, although, well, could happen. So here I have 10 alpha minus 30 alpha. So in total, I'm having 30 alpha is equal to, so 30 alpha is going to go over here, and then 84 is going to go over here, right? So that's going to be 45 plus 40. So 45 plus 40 minus 84. That works out to 1. So that means that alpha is going to be 1 over 30. So if with probability 1 over 30, even though a person from group B is classified as high risk, I'm going to say no, they're not going to be arrested, then I'll get accuracy parity. Okay? Now, it should be clear, and you can try it and see that if I do that, then my nice positive predictive value parity is now going to be violated. Why? Well, because before it wasn't violated, so if I change anything, probably it's going to start getting violated.